So now the question is, will A star search find a solution? So basically I'm asking, is it complete? Will it find a solution if a solution exists? Most people are nodding. The answer is yes, subject to whatever the heuristics are. So you need to have a decent heuristic. So is it guaranteed to find the shortest path? That depends on the heuristic, but if it satisfies certain conditions, the answer is yes. What's the time complexity, space complexity, and how does the goal affect the search? So now, if there is a solution, A star will always find an optimal solution as long as the following conditions are met. So we need to have the branching factor B finite, as with all the other search methods. We need to have those edge costs to be bounded above 0, so they must be positive, so very similar to UCS. And the heuristic function must be greater than or equal to 0, and it must not overestimate the cost of the actual shortest path from that node to the goal. Where have we seen this already in this lecture? What do we call this? Yes, excellent. And we have it here as well. So we've seen these conditions before, and it is that a heuristic is admissible if it never overestimates the cost of the goal. So therefore, if we have an admissible heuristic, one that does not overestimate the actual cost from the current state to the goal, then we actually will get the optimal solution. Here you can see a proof of that. So it takes a little bit of getting used to getting your head around it. So P is a path, and so we have the following. So if a path P to a goal, so that P is a path all the way to the goal, when it's selected from the frontier, can there be a shorter path to the goal? So basically the question is, when we take a node from the frontier and we perform a goal check, is that going to actually be the optimal solution the first time we get to the goal? Suppose path P dash is on the frontier. So we have another path on the frontier. Because P was chosen before this other path, P dash, and we know that by at the goal, the heuristic must be 0, so HP equals 0, we have the following. So to take it off the frontier, that function, f of n, which is g plus h, so that's here, so g plus h, which is 0, we know that this for p must be less than for p dash. So this f, so gp dash plus hp dash, this one here is less than this. Now, because we have an admissible heuristic, so h is an underestimate, that means that if we have any other path, p double dash, to a goal that extends from this other thing that's in the frontier, we know that because h is an underestimate, for this, because it's to the goal, it has plus 0, it must be, by definition, less than this other path. That means that the node that we select off the frontier first must be less than any other for any path p double dash to the goal. So the node that we select from the frontier will be the shortest path to the goal. It will be the shortest path to the goal, so compared to any other thing that is on the frontier. So that's basically a proof that if our heuristic is admissible, we will get the optimal path. We will get the shortest path to the goal. It takes a lot of getting your head around, but basically you just take it as a fact that if your heuristic is admissible, you will get the shortest path to the goal. Here's some extra working, but I think that makes less sense. So how do good heuristics help? Let's think of these examples here. So suppose C is the cost of an optimal solution. What happens to a path, P, where we have the following? So if the path so far plus the heuristic is less than the true cost, what happens? That's basically an admissible one. What happens when it's equal now? So I think it's easier if we think of this. So if our estimate plus the cost is equal to the actual minimum cost, what does that mean? That means our heuristic is exactly estimating the true cost. What would that mean in terms of search? What's the implications of that? So if we have a heuristic that can exactly approximate the remaining distance to the goal state for every path, what does that mean? It means that when we're selecting the nodes, yep. Not yet, when we get to P, not yet. So we're at P so far, so we have some path, and we've got some estimate, H, from P to the goal state. And we're saying that exactly, the path cost so far plus the estimate is exactly equal to the true cost. Pretty much, yes, that means that when we're expanding our nodes from the frontier, using that priority function f, which is g plus h, we know exactly which the next node should be. So as an example, in this here, so when we have these nodes on the frontier, if we have some cost here, which is the actual cost plus an estimate, and that was the true cost, it'll be exactly like this example by chance, where the nodes that we're taking from the frontier will go exactly in the direction of the goal in the shortest path. However, if we had that, it means we wouldn't need to do search because we already have the answer. Okay, so now what happens if we overestimate? So if our heuristic is overestimating the cost, what could happen? So what actually may happen? Yep. Yes, so it may actually fail to find the goal. And the reason for that is that heuristic may be misleading. It might be directing it in the wrong direction. So when it's selecting nodes from the frontier, if it's overestimating for the ones that are close, it might be going in the wrong direction. So how can a better heuristic help? If we're closer to C, it means that when we're expanding those nodes or taking them off the frontier, so when we're doing search, we're going to have to search through less nodes if we have a more accurate heuristic, H, and we want it to be either equal to, in an ideal case, or less than the true cost. So now here we've got an example of something where, for revisiting nodes. So here we have a loop where we have to search through less nodes if we have a more accurate heuristic to where the nodes that we're taking from the frontier will go exactly in the direction of the goal in the shortest path. However, if we had that, it means we wouldn't need to do search because we already have the answer. Okay, so now what happens if we overestimate? So if our heuristic is overestimating the cost, what could happen? So what actually may happen? Yep. Yes, so it may actually fail to find the goal. And the reason for that is that heuristic may be misleading. It might be directing it in the wrong direction. So when it's selecting nodes from the frontier, if it's overestimating for the ones that are close, it might be going in the wrong direction. So how can a better heuristic help? If we're closer to C, it means that when we're expanding those nodes or taking them off the frontier, so when we're doing search, we're going to have to search through less nodes if we have a more accurate heuristic, H, and we want it to be either equal to, in an ideal case, or less than the true cost. So now here we've got an example of something where, for revisiting nodes. So here we have a loop where we can either go A, C, D, G, or A, B, D, G. So this takes a bit of time to go through. Right, so let's do 8-star search using the following. Okay. So I'll try to draw it out as accurately as I can. So sometimes there's direction on these arrows, sometimes there's not. If there is direction, it means it's a directed graph, which means there's only one way to go from one state to the other. So it means it can't go back from B to A. So A, B, C, D, and G. So the initial state is A, and the goal state is G. And we have the true costs in red, which are 1, 2, 3, 4, 100. And we have some heuristic functions, which are 5, 90, 100, and 90. All right, so let's do A-star search. So we have our frontier, which is a priority queue. And we have our, so here I'm going to use the explored set, which is the one way you can do it. So I'll show why we might want to revisit nodes. Okay, so let's start off. So we have A with a cost of 0 plus 90 equal to 90. Okay, so we add that. Okay, so we take it off, and then we expand that, and we get B and C with a cost of 1 plus 100 equals 101, and C with a cost of 2 plus 5 equal to 7. Okay, so now what do? We take off the lowest cost, so we take C, it's explored, and now we get D, and we have that as a cost of 6 plus 90 equals 96. Now in the next lowest is D, and we get G, the goal state, with a cost of 106 plus 0 equals 106. If I make any errors, please let me know. And now we'll take off B, and we get D, and what we notice is that in some representations, you wouldn't explore it again because it's already been explored. So in breadth first search, you don't re-explore nodes that have already been explored because the first time you go to them, it's the shortest. However, here you can see that we do need to actually go to D again. So D with a cost of 1 plus 3 is 4 plus the heuristic, which is 19. That equals 94. And then we take that off. And so we explore it again, and we get to G with a cost of 104 plus 0 equals 104, and then we take it off. So what I want to show here is this heuristic function, which has actually led us the wrong way. So here it told us to go this way, which was actually not ideal. And so what you can see is we had to actually revisit this state. And so it's important in this particular case, where you have a what we call consistent heuristic, that it does need to be revisited again. So I'm going to go to the next slide and show you what I mean by that. So it turns out the shortest path was 104. And if we'd gone the wrong way by our misleading heuristic, it would have been 106. So what we have to do is actually look at nodes multiple times. So there's this optimality versus complexity. So in some versions of search, you actually don't revisit nodes that you've already visited before. However, we see that we do need to revisit it if there was a shorter path there. That's why it's important. It turns out, if you have a consistent heuristic, you don't need to research a node again. And what I mean by consistent is that it obeys the following thing. So this is also called a monotonic heuristic. So a heuristic is consistent if it follows the following. So if for every node and every successor of that node, the estimated cost to reach the goal from n, so the heuristic, is not greater than the step cost plus the estimate from the next node. And so that's called the triangle equality. So you can see it here. So from node n, the estimate, h of n, must be less than or equal to the cost of going to another node plus its heuristic. So it's basically showing a visual representation of what a consistent heuristic is. If it's consistent, it means that you won't need to revisit nodes that have already been visited before. So that means in that case, what we had before, we don't need to visit D again if it's already been visited, because the first time we get there, it will be the lowest cost. So this is important when you have loops. Okay, so if the heuristic is consistent, when A star expands a node n, for example, node D before, the path to n is optimal. In this case here, we had a non-consistent heuristic. So if a heuristic is consistent, it is admissible, but not the other way around. So how do we check for consistency? We check if this holds. So let's do that on the example. Yes. No, because there's no up arrow. So this is so this arrow here is only going one way, so it goes only this way. Because we went via node B. So this one here, so this is a node D, which actually has a parent. Its parent was B, so it was ABD as a full path. So remember, these are actually nodes that represent the full path. So this D here was from C and A. Yeah, so great question. And that's how we got the 4. So it came from A, B, D path. All right, so now let's check for consistency. So check consistency. So you have to check it for every branch. So let's check it of branch A to B. Okay, so the heuristic of A must be less than or equal to the cost of A to B plus the heuristic of B. So that's just that triangle inequality. So we have A, we have B, we have some heuristic for B, we have some heuristic for A, and we have some cost that takes us to get from A to B. Okay, so what are those values? So the heuristic of A is 90. It must be less than or equal to the cost of going from A to B, that's 1, plus the heuristic for B, which is 100. Is 90 less than or equal to the cost of A to B plus the heuristic of B. So that's just that triangle inequality. So we have A, we have B, we have some heuristic for B, we have some heuristic for A, and we have some cost that takes us to get from A to B. Okay, so what are those values? So the heuristic of A is 90. It must be less than or equal to the cost of going from A to B, that's 1, plus the heuristic for B, which is 100. Is 90 less than or equal to 100? Sorry, 101? Yes, so that branch there is consistent. Let's check another one. So branch, so same thing, but for A to C. So heuristic of A must be less than or equal to the cost of going from A to C plus the heuristic C. Let's plug in those values. So 90 must be less than or equal to the cost of A to C, which was 2. Sorry, I can't see it anymore. And the heuristic was 5. So is 90 less than or equal to 7? No, not in this world. So that is not consistent. So it's not consistent, therefore we need to revisit nodes. Any questions? So if the heuristic is consistent, when A star expands that node, the path to that node is optimal, and therefore we don't need to revisit nodes that have already been expanded. And if it's consistent, it means it's admissible, but not the other way around. So if something's admissible, it does not necessarily mean it is consistent. All right, so now the last part before we get into a break is how to generate heuristics. So typically to design heuristics, you need to know something about your problem. So as you saw with the maze, we know what the cost would be if there was no obstacles, for example. So we can use approximations. So we can use, for example, Euclidean distance could be 1. We could use Manhattan distance, which means that you can only travel up or up, down, left, right, so in those coordinates. You can also know knowledge about the subproblems, and you can also learn from prior results of solving the same or similar problems. So we have some examples. So as I mentioned before, Euclidean distance. This is just the standard distance that you or I use every day without even calling it Euclidean distance. So if I was going from here to somewhere else, let's say on a map, it's the bird's eye distance. It's a straight line between those points. If you're looking at the globe and you're going between points, it'd be the geodesic distance because it'd be around that surface. Then for other examples could be Hamming distance, Manhattan distance, and for the A puzzle, one approximation you could use is something called the number of inversions. So in this week's tutorial, that's going to be an exercise for you to do at home because there won't be enough time to complete it, but you can try that out as an example. You already have it implemented as part of tutorial 2. All right. So there's a couple of other points I want to mention in terms of heuristics. So in the assignment, what can you see? So like what kind of distance are we going to be using? So you need to look at the documentation. That was homework for you for when I sent out the Blackboard announcement. Probably many of you haven't had a chance to do that yet, but your task was to look at what the state representation is and to look at what the action costs are. They're in the document I provided. So you can see here. So there's 4 actions that the agent can do. So it can go forward, it can go backwards, it can spin left, spin right. So basically rotate clockwise, anti-clockwise. And then each of those actions has a different cost. So there is some action-based cost, which is given in the source code. And there's also an additional cost if it's trying to push a honey widget. So that's called the action push cost. So you can see the base cost, forward costs 1, reverse costs 1, spinning left costs 0.1, and spinning right costs 0.1. So spinning on the spot isn't very expensive. Moving forward and backwards is the same cost if you're not pushing a widget. However, if you are pushing a widget, you add this extra cost. All costs would be in a hexagon. You can literally just really complicated. But you can actually create a function that calculates these costs. So if you have a state where the agent is here and it wants to get to here, you can compute a function that will calculate this cost. So you can multiply the steps by the cost in the specifications. So this will be highly useful in the design of your heuristics. Another consideration you'll have is in this particular example, we only have one widget and one target location that it could go into. But if you look at some of the other environments in the test cases folder, sometimes we have multiple targets. So you might need to consider that there would be a different order that you need to go into these. So here we have this widget and this widget here. Then you need to move on to this honeycomb and this honeycomb here. If you're designing a heuristic, you want to get something that doesn't overestimate the cost to the goal states. So if you are using a human intuition, you need to play around with this to figure out your human intuition, but you need to at least get to the target and then pull it or push it to these targets. So you know what that minimum cost will be. So you can calculate the heuristic function given some state of the game. And one thing that you could consider is some form of traveling salesman problem. So it's very well known. Yes, it can be challenging. You can just do a brute force solution of that. So what traveling salesman problem means is that part of the solution. So caching is quite important to do. What do I mean by caching? Very similar to what we're doing with these visited or reached states. You have some state and you have some cost. That was the path cost. You could do exactly the same thing with the heuristic function. So as an example, you might have some heuristic. So you check if the state is already cached in your heuristic cache. If it is, you just return that value. If not, you can calculate the cost. So self-modified distance. Here I call it modified distance because it's not actually the number of steps in your hexagonal grid, but it might be a multiplication factor by that. And then you just add it to your cache whenever you calculate it. So that's what I mean by caching or caching. So you'll see this, some parts of this as part of this week's tutorial. So make sure to attend that. If you can, do it early because try it out on your own because then you'll have good questions to ask. We're going to have extra support in the tutorials next week because we lose the Echo holiday. So we're going to have extra tutors on the other sessions. Any questions? No. Okay, so this is a good point to have a break. So we'll group back in about 4 minutes to make it a nice round number, and we'll jump into the next module. If anyone has any questions, please feel free to come up. Otherwise, see you in about 4 minutes. Very similar to what we're doing with these visited or reached states, you have some state and you have some cost. That was the path cost. You could do exactly the same thing with the heuristic function. So as an example, you might have some heuristic. So you check if the state is already cached in your heuristic cache. If it is, you just return that value. If not, you can calculate the cost. So thanks, everyone. I've got a quick question. Does anyone have access problems to get to Echo Poll? So I've had a few people email me. I think some of them, they went in the roster at the time that I'd synced it last, so now that was synced since I sent my announcement. Just accessing. To test your knowledge, I created this. All right, so this is just to quickly test your understanding. So most people have already done this. Whoops. The image is gone. Did this happen when you guys did this as well? No, I don't know why it's not appearing. I'll play. No, I don't know why that's not working. Echo Poll doesn't seem to like me. Anyway, this is what it's supposed to look like. I don't know why it's not there. Okay, so just to test your own knowledge, you don't need to do it again if you've already done it. So which shaded goal will depth first search or DFS find first out of the following? So assume the order of node expansion is left to right. So if we're looking at depth first search, which of the following nodes will be expanded first? You can all say that some people are actually logged in, great. Right, then, yeah, great, 100% accuracy. Then D, yeah, correct. Some people are actually logged in, great. Right, then, yeah, great, 100% accuracy, great job. Now breadth first search is a task. So what will be the node that will be found? So log in, and complete. So we have a lot of definitions in this course. Completeness is one of them. So a complete search algorithm is a search algorithm that guarantees to return the optimal solution. Shake or nod? I think shake, excellent. Got like very fast response time. The last one was a very complicated one. It required many steps of thinking and it wasn't worded very well. The student who posted on response time. So for the graph, be the priority cost f of n, use using building is, it will actually appear with the shortest path. So it will be, so we're looking at what's the priority cost f of n. What is it in uniform cost search? So is it, it will be the path cost, g of n. So the path cost, 65. You would about, the here's path cost. Proportions, a little bit of an extension from search. So it's a different kind of search. All right, so in terms of what we're going to cover in, we're going to have 1.5 lectures on this. So we're going to cover constraint satisfaction problems, use as part of that, and then we're going to cover logic, so propositions and inference, and then loop back to satisfiability again from the lens of logic. Introducing constraint satisfaction problems. So a constraint is actually a subset of search problems. previously about the environment or the world that the agent operates in. So it's single agent, deterministic actions, fully observed state, discrete problems. So in terms of problems, we have various types of puzzles. So many people would enjoy students enjoy playing these types of games. That's one of the things that attracted them to AI in the first place. So some common CSP problems include things like the 8 puzzle, where you have, the 8 queens puzzle, where you have queens that you need a chessboard without any of the queens. We have Sudoku that can also be modeled as a constraint satisfaction. And it's like that, adjacent states. And then there are also many constraint satisfaction problems. For example, timetabling. You have various constraints, and you need to figure out the offerings so that the constraints aren't violated. You'll see that sometimes those are violated. So some people that take very rare combinations of courses, even here, might only have the option of a clash between 2 lectures, and they have to pick a delayed viewing. Turns out here, and actually hundreds of different programs that, for example, one class cohort can do. Things like transport scheduling, factory scheduling, inferring time based off the context, and of search problems. And in particular, they are a type of identification problem. And what I mean by that is it's the task of providing assignments to variables. So in these types of problems, the goal itself is important and not the path. So compared to the search that we've looked at so far, where we've actually considered the minimum path cost, we instead only want to look at whether it satisfies the constraints. And in most formulations, the paths are all the same depth. Because basically you've got a set of variables that you need to assign, and each row represents every combination of variable assignments. Assignments to that variable. And then at the end of the first part of this module, which is on CSPs, you should be able to do the following. So recognize and represent CSPs, show how constraint satisfaction problems can be solved using search. So you will see depth first search again, and then some extra ways to make it more efficient. So you should also be able to implement and trace arc consistency of a constraint graph. Okay, so the formal definition of a constraint satisfaction problem is that we have the following. So we have a set of variables that we want to assign values to. The values they have an associated domain of values that they can take. So that's the domain of that variable. And we have a set of constraints on various subsets of the variables, which are what we call logical predicates. So connections between 2 things that can either be true or false. And that specifies legal combinations of values for those variables. Actually, it can be more than 1. It just basically is logical means binary, so 0 or 1. And a model, the terminology that we use is called a model of a CSP, is an assignment of values to variables that satisfies all of the constraints. So that's the formal terminology. I think if you just look at the words constraint satisfaction problem, you have a set of constraints, you have a set of variables, you need to assign values to those variables without violating constraints. So it's quite simple, but that's the formal language that we use. So variables, domains, constraints, and a model. There's also another class of problems called constraint optimization problems, and that's not where you just do satisfiability, but instead you might have a cost function for assignments to different variables. For example, let's say when you're assigning your own timetable, there might be things that are satisfiable. So let's say you could have a class at 8 a.m., a class at 6 p.m., and it doesn't have any constraints, so that means there's no overlapping classes. However, there might be some timetables that are more desirable than others, so you can assign costs. For example, between like an 8 a.m. class is horrible, and so you assign it a high cost. So that's a different class of problem. And so in that one, you minimize a cost function. But here we're only going to be looking at constraint satisfaction problems and not constraint optimization problems. All right, so here we have an example of scheduling activities. So we have some variables, so A, B, C, D, E, that represent the starting times of various activities, and the domains, so the values that those variables can take, are 1, 2, 3, 4 for all of them. And these are the constraints, so they are the conflicts between the variables. So B can't be 3, C can't be 2, and there can be relationships between the different variables as well. So C must be less than D, etc. So this could be things such as, let's say you've got 10 tutors to tutor an AI course, and let's say some people might need to not work with others, for example, or might not be available at a certain time. So that's what these constraints could mean. So here we have another example of a graph coloring problem. So in this problem, you assign each state or territory, because Australia has states and territories, a color such that no 2 adjacent states have the same color. So here we can see an example solution to that constraint satisfaction problem. So now let's check your knowledge of the definitions I just gave for this problem. So what are the variables in this case? So yeah, I can hear people saying the states and territories. So basically these things here. And what are the domains? So what are the values they can take? So I haven't defined those, but it's red, green, and blue. And what are the constraints? So you can actually model this and say, okay, Western Australia. So I can hear people saying the states and territories. So basically these things here. And what are the domains? So what are the values they can take? So it can't be the same as Northern Territory, and Western Australia can't be the same as South Australia, etc. So here we can see that we can convert this into a graph very similar to search problems that we were looking at previously, and we have the following variables. The domain, we have, it can be red, green, or blue for each of those states or territories, and we have the following constraints, which are a lot. So all of these lines between these things represent the constraints. Okay, so now let's look at Sudoku. I did make this into a echo poll activity, but I think it's just easier if we just do it by, not by hand, but just out loud. So what are the variables here? Yeah, exactly, perfect. So it's each of the empty squares. So assuming that some are already set. What are the domains? Yeah, exactly, the integers 1 through 9, and what are the constraints? So if anyone's played Sudoku before, they know that in each row, column, and square, there can only appear once the numbers 1 through 9. So that's what the constraints are, and they can be represented mathematically using those logical predicates. Okay, so now how do we solve such a problem? These are toy problems that we're looking at, but you can actually solve much larger problems like a timetabling system for a university, for example. Okay, so one way we could do it is a very naive method called generate and test. So basically we just set some assignment of the values to those variables, and then we check, are any of those constraints violated? And we could do that for every single combination until we find one that is satisfiable. So we just need to find out whether it is satisfiable or not, so the constraints that we have. But the state space is huge. So we have the domain of variable 1 multiplied by the domain of variable 2, etc. And that's called the Cartesian product, which you would have seen in assignment 0, and so that is exponential. So again, this to the power of n. So you test each assignment with the constraints. And then how many assignments do we need to be tested for n variables, each with domain size d? So we can see that our domain, so that would be d, which is quite a large number. How many assignments would we need to test here? Just n times d into d to the n. So you could probably calculate. So each of those domains could take on any n value, so any n by any n by any, or sorry, any d by any d by any d, n times. So for this example, we can see that it'll be however many leaf nodes there are in that big tree of the assignments. So in this case, it can be any of 3 values, r, g, b. So d multiplied by d multiplied by d, so 7 times, that's 2,000. So this particular problem isn't that big. We could actually test everything with a brute force solution, and it would only take 2,000 different options. So the other thing that we can do is naively apply depth first search to this problem. So what I mean by that is each row of our search will be some assignment. So variable, so you might assign, for example, red, green, or blue to this variable, and then the next variable will have either red, green, or blue, and then so on and so forth. So eventually we'll have all those leaf nodes of the tree. That's that. So that's what I mean by the leaf nodes of the tree. So if you actually expand it out. Whoops. So the states are defined, so the states in our search tree are defined by the values assigned so far, and that's what we call a partial assignment. So we might have, for example, Western Australia, equals to red, and something else. And initially we start off with no variables being assigned anything, and then we have some successor function which assigns a value to an unassigned variable. And then the goal test is check whether the current assignment is complete and satisfies all of the constraints. So that's what I mean by converting this into a search problem. So basically we have each of those levels as an assignment of a value to a variable. So what can go wrong? Goal test is, and initially we start off with no, so you could, is huge. So we have the domain of variable 1, multiplied by university, for example. Okay, so one way we could do it is a very naive method called generate and test. So basically we just set some assignment of the values to those variables, and then we check, are any of those constraints violated? And we could do that for every single combination until we find one that is satisfiable. So we just need to find out whether it is satisfiable or not, so the constraints that we have. But the state space is huge. So we have the domain of variable 1 multiplied by the domain of variable 2, etc. And that's called the Cartesian product, which you would have seen in assignment 0, and so that is exponential. So again, this to the power of n. So you test each assignment with the constraints, and then how many assignments do we need to be tested for n variables, each with domain size d? So we can see that our domain, so that would be d, which is quite a large number. How many assignments would we need to test here? Just n times d into d to the n. So you could probably calculate. So each of those domains could take on any n value, so any n by any n by any, or sorry, any d by any d by any d, n times. So for this example, we can see that it'll be however many leaf nodes there are in that big tree of the assignments. So in this case, it could be any of 3 values, r, g, v. So d multiplied by d multiplied by d, so 7 times, that's 2,000. So this particular problem isn't that big. We could actually test everything with a brute force solution, and it would only take 2,000 different options. So the other thing that we can do is naively apply depth first search to this problem. So what I mean by that is each row of our search will be some assignment. So variable, so you might assign, for example, red, green, or blue to this variable. And then the next variable will have either red, green, or blue. And then so on and so forth. So eventually we'll have all those leaf nodes of the tree. So that's that. So that's what I mean by the leaf nodes of the tree. So do you actually expand it out? Whoops. So the states are defined. So the states in our search tree are defined by the values assigned so far. And that's what we call a partial assignment. So we might have, for example, Western Australia, equals to red, and something else. And initially we start off with no variables being assigned anything, and then we have some successor function which assigns a value to an unassigned variable. And then the goal test is check whether the current assignment is complete and satisfies all of the constraints. So that's what I mean by converting this into a search problem. So basically we have each of those levels as an assignment of a value to a variable. So what can go wrong? Anyone? So this particular problem I said was relatively small, where it only had on the order of 2,000 leaf nodes. But if we have more than just 3 colors that we could assign, a much larger problem, we actually have to remember each of those assignments. So we're basically, even in depth first search, we have to remember all the things that we've assigned so far. It can become very, very large. And so even with depth first search, that's memory that we need to store those partial assignments is actually very large, and it grows exponentially. So one thing we could do instead is backtracking depth first search, which I mentioned a couple of lectures back, but that's where rather than actually generating all the nodes, you basically go only generate as it goes, and then you backtrack up, and then you generate, and then you go back. So you just have to, it's a little bit of a more memory efficient way to do depth first search. So in backtracking algorithms for constraint satisfaction problems, we systematically explore the domain by instantiating the variables one at a time. So basically, you go Western Australia equals red, then New South Wales equals green, whatever. And then you evaluate each of the constraints as soon as all of its variables are bound. So once the variable is set, you check whether any of those constraints are violated. And then any partial assignment that doesn't satisfy the constraint can be pruned. So let's say you've assigned red and Northern Territory red as well. So that is a constraint violation. It can be just pruned and not stored in memory anymore. So here we have an example of a scheduling assignment. So we assign a equals 1 and b equals 1. That's inconsistent with the constraint a not equal to b, regardless of the values of all the other variables. So here we have an example of the backtracking algorithm. So here's what I was trying to draw very roughly, but here we have a much nicer demonstration of that. So we start off with the starting state, which is nothing has been assigned yet. So none of our variables have a value assigned to them yet. Then what we do is we have each of these. So we have Western Australia, red, green, or blue. And then you can see here, we then color in Northern Territory, and we don't actually put in red because that's a violation of the constraint between these two states. It's confusing because the states here in Australia, that's like states and territories when we're calling them states of our constraint satisfaction problem. And then here you can see that you go the next one, and so that is Queensland, and it can be either red or blue. What you can see is each of the levels, so this is one variable, so that variable is Western Australia. Then the next row is Northern Territory. Then the next row is Queensland. So that's what this search tree looks like. That's what I was trying to very roughly draw on my iPad. So that's how the search progresses, and you can see that with a very simple backtracking algorithm, this is what it would look like. So we just don't add the very simple constraints as you're building it. Now, does this state here have any valid successors? No, because we can see there's no color that we can assign here that will not violate the constraints. So it can't be red, can't be green, can't be blue. So therefore, that would go backtrack up, and then it would try to continue down here. So a constraint satisfaction problem can be solved by graph searching with variable ordering and fail on violation. So similar to that, where we know that this is not allowed, so then it would backtrack up. So a node in this search graph is an assignment of values to variables. So that will be a partial assignment. And then suppose node n is the assignment as follows. Then you select a variable y that isn't assigned in n. So you can use whatever your favorite graph search algorithm is. And then for each of the value in the domain, you add that as a neighbor if it's consistent with the constraints. So that's basically just writing what we've done here in words. And so the start node is an empty assignment, and then a goal node is a total assignment that satisfies the constraints. So at the bottom of this tree, you'd have all of the states colored where there are no constraints. So there'll be no touching states that have the same color. And so here is a recursive implementation of backtracking search. So it's basically just what we call backtracking depth first search. So as soon as it violates, you roll back up the tree, and then you try out the next option, then you roll back up. And so it's a more memory efficient way to do it. All right, so I'm just going to go quickly through this Sudoku example, and then we'll leave the next parts to next lecture. So we're doing our partial solution. So we have, so far, we've got the assignments here, so 4, 6, 7, 3, 8, so the ones that are not as bold. Now we get up to the following. So this is row 2, column 5. So we give it some assignment. So we have our partial solution so far, which is the assignment of the variables that we've got so far. And now we're up to state 2, 5. And so that is here. So can we assign it a 1? No, because we already have 1. Can we assign it a 2? No. A 3? No. Can we assign it a 4? Yes. So we put in a 4. Now we're going in this depth first search manner. So now let's go to the next one. So we have 2, 7. All right, so can this be a 1? Yes, because there's no violation. All right. Now we go to the next state here. So 2, 8. Okay, so it can't be a 1 because I've just assigned that a 1. Can this be a 2? No. Can it be a 3? No. This one we just put a 4 in, so it can't be a 4. Can it be a 5? No. 6? No. 7? No. 8? No. 9? No. So it turns out nothing can go here. So in our depth first search, we go back up the tree until we have a node that is unassigned. So we go to here, here, and we try out a different option. So now we try out a, what can this one be now? 1, 2, 3, 4, 5, 6, 7, 8. So that one can be a 9. All right, so now this is a 9. Now what can go here? So 1, yes it can. Here, 2, no, 3, no, 4, yes. And so you basically just continue through that. And so you keep doing this search. And so once you get a violation, you backtrack up the tree, and then you do a reassignment of the variables. So that's basically going through this backtracking search. And we'll leave it there. I also had an announcement on Friday after our tutor meeting for the assignment 1 code. But by this stage, you should actually be able to fully implement UCS because you have the solutions to tutorial 2. So I would actually suggest completing that because A star is going to take you a lot longer. So for the assignment, you can already complete uniform cost search and spend a bit more time on A star search. So good luck with that, and see you next week.
Sitting in the front row. Love it. Sit here every week. Hey, can you hear me up there? Yep. Yep, awesome, thank you. Hello, welcome back. It's week 4. I'll get started slowly with some housekeeping. Who's working on the assignment at the moment? Who's posting on Ed at the moment? Yeah, okay, so firstly, sorry, Ed has like 600 posts. We're struggling, to be honest. We're inundated, so we're trying to get through things as best we can, but please bear with us. If you think that you asked a question like a week ago and we didn't resolve it, just ping the thread because we really have lost track. I try and keep them unread until I can answer them or the other tutors answer them. But like I said, I think we had 200 posts in the last 48 hours, so we're kind of having a really hard time keeping a lid on everything. I see a very, very more sparse lecture theatre than usual, so I suppose that some people are using this 2-hour block to maybe work on their assignment. Totally understandable. So the first few things I want to say, just housekeeping. Ripple, there isn't a Ripple for this week, right? So you did your moderation already, and then there's a week off for you to do the assignment because it's due at the end of next week, so next Friday, 4 p.m. So you've got about a week. And then there'll be Ripple due after that. So just keep in your mind that you need to do RIPL, but the next one's easy. You just have to go and do some questions. So the whole point of RIPL was to make questions for you to do, so now you can go and do them. I know you're all excited about the assignment. I'll give you some more help today. Speaking of, I have some updates for the assignment. No, I'm not breaking APIs. Don't worry. No more of that. Someone called me out on that last week. Okay, so the updates are as follows. Firstly, Gradescope is up and running, but we need to still tune some time. So if you're having problems with your timeouts, you're getting burned by our welcome to 3506 tests, there's a chance we might add another second or two. So you might sneak in. You might not. We're going to tune them a little bit. So they're not going to get worse. They're not going to get harder. They might get a little bit easier. They might not. Okay, so just keep an eye on that. For the last part, who's working on K-MERS already? Oh, goodness. Okay, not many people. So in K-MERS, you'll notice that sometimes we give you a Python list, and we say do something with it. And in one of the queries, we actually say, please give us back a Python list. We're going to let you use Python lists for those. So if I give you a Python list, you can use len. You don't have to iterate the list to check the length. Currently, that's what people are doing. If we ask you to return a Python list, you've got your dynamic array. A bunch of you have probably written a function that says convert my dynamic array into a Python list without nuns in the middle, return it. You can just return a Python list. You can still do what you're doing, but you can just use a Python list if you want. That's only for K-MERS. If you use Python list anywhere else, you're in trouble. Okay. Other things, so some people are having trouble with the timeouts. My advice to you is as follows. The way we write tests is like this. We get your structure. We instantiate an object. We go around a for loop a million times. We add an element, or we flip a coin, an n-sided coin, and if the coin's 1, we add an element. If it's 2, we delete an element, or if it's heads or whatever, n-sided coin. If it's 3, we delete the first element. If it's 4, we prepend something. If it's 5, we reverse, so on. So if you come to us and are like, oh, I'm failing a test, but I did a bunch of appends and it looks good to me, well, you need to do other stuff too, right? So make your tests big, make them kind of more exhaustive, import random, do a bunch of stuff. Don't hand roll a 5-line test and say it's working, right? If I had $1 for every student that said that my code works and we checked and it doesn't, I would have at least $3. Maybe more. Okay, so there's that. And also, if you're thinking, hey, I think I should be passing this, my code's looking pretty good, what it could be is your data structure might suck. It's possible. Okay, so suppose, for example, here's a hint. I give you a big list of stuff. If you go through the list and do append, well, if you're doing a amortized insertion, you're going to do a resize, and then when you get full, you're going to do another resize, and then you're going to do another resize. But if you already knew the size of the things I was going to give you, why not just allocate that amount of space and put the stuff there? Or why not just take that list from me and say, I own that list now, Joel, that's my list. Okay, so these are micro optimizations, but the point is copying data is not free. It's linear in the copy you do, so minimizing that might help. Okay, so they're the main things. I'll make an updated spec with the K-MERS rules that I've just told you about. If Gradescope is actually crashing, that does happen. Poor Gradescope, they get 600 submissions at once and their server on AWS or whatever spins up all these machines and they run them. Sometimes they explode. It does happen. So if that happens, you can try and resubmit. If you keep getting crashes, then you're allowed to make an echo saying my Gradescope's like blowing up, please help. Question? Yeah, this is a great question. So the question is, does the amount of traffic on Gradescope affect the latency and the timeouts of the experiments? It can. And so what we do when we're finished with the assignment is we go back through and run every one individually, and we run them 5 times. So we take the highest mark of 5 runs of your assignment to make sure that we mitigate for any sort of server issues and things like that. Yeah. So, and we try and make sure that if something goes really wrong, we'll run it again. So we try and be fair in that way. Yeah. Gradescope's always running tests, not just from us, from everybody, but they scale out, right? So they're not just running on my office computer. Gradescope use like AWS or Azure or something, and when they get submissions come in, they get fed out to virtual machines on real servers, and they scale as they need to. So you should be getting access. Gradescope tell us, we're giving you all, I think 8 gig of RAM machine with, I think 4 cores. So you should all be getting access to reasonable hardware, but that doesn't mean it always happens, because if they're trying to scale while you submit, maybe your thing gets stuck in a queue, bad stuff happens, so on. But we're trying our best to be fair, and that's what we did last year, and we think it works, so you need to trust us. Yes, you need to trust us. Any other questions on the assignment? We are having the help session at 4 right here, so if you can stick around, we'll have some more tutors myself here to help. I will talk about bit vectors up front. I wasn't going to, but people don't like them very much. For a little bit of comedic relief, a couple of weeks ago, somebody posted this, and I thought it was very funny. And they said, "Oh, this is like a log n algorithm." But to me, this looks like merge sort when you merge. Now, speaking of merge sort, some poor student who I've changed their name, they accidentally sorted their sort function file, their dynamic array. And unfortunately, they hadn't done a git commit before they got their merge sort working. So actually, it works because the thing's sorted, but they lost their file because now their file is sorted. And I said, "This is actually so funny. I'm so sorry." So this is, yeah, look, it's so over. Yes, it is, unfortunately. But hey, at least you got merge sort working. This poor student, I changed their name, but I won't tell you who they are because this was a private post. But I'm very sorry this happened to you, but it's very funny. Okay, I'm very sorry. But you did it once, I'm sure you can do it again. And to everybody else who hasn't done merge sort, if this student can merge sort their own file, then so can you. So please commit your changes. Okay. All right. I'll come back to this. So at one point when I joined UQ, I taught the course INFS 3200, which is Advanced Database Systems. And a part of that course had a little tiny bit about indexing with bit vectors. And so I did a little tiny bit of a lecture about bit vectors. And because I'm lazy, I lifted that portion of that lecture out and now I'm showing it to you now. Okay, so I'm going to tell you about bit vectors before we move on from linear structures and do a bit more interesting stuff today. So this is confusing a lot of people, and I'll try and get it straightened out now. But basically, a bit vector, the ADT, right? Who remembers what an ADT is? You all should know this. The abstract data type. So what does that mean? No, someone else? It tells you what the thing should do, but not how to do it, right? So an ADT says, here's the specification. I don't care how you implement it underneath. This is what should happen. So a bit vector is an ADT that behaves just like an array of Boolean values, right? So what you can do is you can insert, and this is a different API to the one we're using, so just be aware. But the point is, basically, the user might say, I would like to append a true, a false, a true, a false, right? And because they did an append true, right? Append true, false, the thing at index 0, right? Because I've append, the thing at index 0 should be that first true, right? So they can ask, hey, what is at index 0? And you say, hey, it's true. What's at index 1? It's false. What's at index 2? It's true. So on. This is how a bit vector behaves. But instead of storing a bunch of Boolean values in a list, because that's going to take way too much space, we can do something a little bit trickier, a little bit more clever. Okay? And what we do, now I'm talking in C, but the same thing applies in Python, we basically use a gigantic slab of integers. Okay? So the idea is that you make, this is like a Python list, okay? Don't worry about the C syntax. This is a list. So that thing, that grey boxes, they're just integers in an array. Okay, you could use a dynamic array for this if you wanted to. So this is the thing at 0, 1, 2, 3, 4, 5, 6, so on. It's just a normal array of integers. Now, if a user comes along and says to you, I want to append a bit to your bit vector and it's empty, what that means is they want to set a bit in the first integer to be a 1. Now, you could set whatever bit you want to be a 1, as long as when the user comes back and says, hey, what's at index 0, you say it's a 1, right? Now, what I mean by that is in this case, I'm saying, look, the thing at 5, at position 5, is a 64-bit integer, right? There are 64 bits here. Suppose we were talking about this one, right? Just suppose we're talking about the first one. If a user appends a 1, you might like to use the least significant bit and set that to be a 1. You might prefer to set the most significant bit and make that a 1. I don't care. And in fact, the user doesn't care either. As long as the user comes along and says, hey, what is at index 0, and you say it's a 1, life's good, right? And if the user says, how many things are in my bit vector right now, you say 1, because they've only put one bit in, right? So if they go append, blah, 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 at some point they're going to run out of bits, right? Because an integer, not really in Python, but in our example, one of these square, rectangle, grey things can store 64 Boolean values, right? So if you have one of those, and a user has done 64 appends of zeros and ones, the next time they append, you've got nowhere to put that new bit, right? So what do? You put another integer in your array, and you set its first bit to 1, for example, or its last bit to 1. Whatever you want to do, it doesn't matter. The point is, it behaves just like a dynamic array with true and falses going into it, right? But it's 64 times smaller, or actually much, much smaller in Python land, okay? So what would we do, right? So here's an example. Suppose I had a bunch of things in here, right? And maybe instead of insert, I want to set the 100th bit, right? I don't know if the 100th bit is 0 or 1, but the user says, hey, I want that bit to be a 1 now. I want to say that the thing at 100 is a 1. How do I do that? Well, I actually already know that if I'm storing 64 bits in a single integer, the 100th bit must be in the first, so the second integer, right? The index 1 integer. So it's in here, because there are 64 bits in here, and there are 64 bits in here. The first 64 isn't enough, right? So it has to be in the second word, right? And so I get that word out. I say, hey, that's the word at this position of the array. And then how do I know whereabouts the bit is inside that integer? Well, I can just take a modulus, right? It's the 36th bit in the second integer, which is the integer at position 1 by index, right? So I get that thing out. And then what do I do with it? So I've got an integer here, right? This is just some int. How do I set the 36th, sorry, how do I set the 36th bit to be a 1? Yeah, I could make it, actually there are many ways, but this is a nice idea. I could use a mask and I could do an int and or, right? So let me remind you of some binary operations. Suppose you've got, that's kind of boring, 1010, 0101. If I'm doing a logical or on these, do you remember what or means? If either bits are 1, I keep a 1, right? If they're both 0, I do a 0, and if they're both 1, I still do a 1. So oring here is 1, oring here is 1, 1, 1, right? So if I or those two words together, those two ints, I get 1, 1, 1, 1. So our colleague here said, why don't we do something like get the integer out, right? So go here, get this integer, we'll call it x, right? We make another integer where the 36th bit is a 1, right? Because that's the one I want to turn on. And then I take the integer here, and I OR them together, and I store the result in x. Because the only difference from x before to x now is that I turn the 36th bit on. And then I put that thing back in the array. I just say, okay, I've updated x, put it back, right? So that's it. That's how bit vectors work. That's all they are, okay? And my whole point here is that position 36, to me, I'm working from the LSB this way. So I'm going to go 36, because we read binary right to left. I'm going to start at the least significant bit, and I'm going to move 36 over to the most. But you might start at the most significant bit and go to the least. I don't actually care, neither does the user. As long as you're consistent, things will be okay, all right? So what this looks like in C, and in fact in Python, is find the integer index, right, step 1, find the bit index, step 2, get the thing out of the array, and set the thing to what you want, which in this case is moving a 1 bit in by a position, which is 36. So you take a 1 bit, move it in 36 places. That's what this does. Do an OR, and OR it with the word you had before, and that does what you want it to do. Life's good. You move on, okay? And this is all super fast. Why? This is a bitwise operator. This is a bitwise operator. These are constant time, right? So all of this is constant time. You look up a word in memory, you get it out, you look up a position, you shift something in, you do an OR. They're all constant time operations, okay? I'm out of space here. So now let me show you. Get the bit vector thing over and done with, hopefully. Last week, okay, you can see, I put this up on the LMS, but I didn't have time to talk about it last week. So if you can't remember how bits work and how operators work and so on, go and find this file called 3-bits.py on the week 3 material. Basically, what I do is, this is just a helper to print a binary number. So when you go to a place in memory, everything stored in computer memory is binary, and that doesn't mean it's a string with ones and zeros. It means it's literally pulses of electricity, right, that are on or off. So this is just a helper so that we can understand what's sitting in memory in a binary string, but you're actually working with real raw binary data. So what I do in this example is I take some single integer, say where it's got 64 bits in it. I check, hey, what's the initial data in this thing? It should be a 0, right? So it's going to print 64 zeros, because 0 in binary is 64 zeros. No surprises, right? Then I say, what's the biggest integer I could have? So that's going to be 2 to the power 64. That's all 64 bits set to 1, okay? And we can print that out as well. So that's going to be 64 ones in a row, okay? So 0 is 64 zeros, 2 to the 64 is 64 ones. And then I say, hey, what if we want to get the first bit out? Or what if we want to set the first bit? Or what if we want to set bits 1 to 13? How do we do that? This tells you how to do all of those things. And it shows you how to do it, and what the data looks like before you do it, and what it looks like after you do it. So I'm not going to run through it all by now, like in the lecture now, because we're going to run out of time. But this is kind of pretty comprehensive, and everything you might need to get a bit vector working, I think, is in here. Maybe not for rotate, but it wouldn't be very hard to extrapolate what I've done here. So what I leave you with is bit vector hint. In this example, I can only get offset 64 bits because I've got one integer. If I want to do more than 64 bits, what do I do? What do I do? I make an array of integers, and I put more integers in there. So for every integer, I can store 64 things. So I just need as many integers as bits I want, right? So that's, I think, helpful. And I think if you run it, you get a scary looking output like this. But you know, it should be pretty helpful. So please go and look at that. Hopefully that's clear. If you're really stuck with bit vector, use a list of trues and falses. So on an act like a bit vector, it's just going to be about 1,000 times bigger, okay? All right, so I don't care which bit you put where, as long as the black box to the user, right, this is really the point I'm trying to make. If they say, I want to know if I've got a 0 or a 1 at index 1,262, if your answer's right, your bit vector's right, okay? That's all. You can store that bit wherever you want. Just don't put it in a dictionary or you'll get in trouble. All right, so what are we doing this week, apart from bit vectors? I actually think this week is kind of boring. Sorry. But there are a few cool things. So the reason it's kind of boring is because we have to go through boring terminology about trees. And the reason we need to do this is because next week we're going to talk a bit more about trees, and then we're going to go to dictionaries and hash tables, but then we're going to come back to trees again, and you're going to need to sort of be able to talk about trees and sort of know what I mean when I say certain things, and you talk to each other and argue in lectures, in tutorials and so on. So there's a bit of that, but also there's a bit of stacks and queues, which, who's heard of a stack before? Who's lined up in a queue before? Yeah, I hope everyone, or you haven't lived. So these are really simple structures, and we'll be able to get through them really quick. This is probably my favorite slide in the whole course. Think of a spring-loaded plate dispenser. Who has one of those at home? What? You have one, okay. He has a collection of, your mum has a collection of spring-loaded. Okay, so there's a data structure maybe that's a collection of stacks or something. I can't think of a good joke here. Yeah, okay, yeah, nice, give me an example. A stack of weight plates or something on the floor, right? So stacks are exactly what you think they are. You have a bunch of stuff, right? I don't really know what the stuff is, or I don't really care, but you can only get the top one off at a time, right? So you can put a bunch of things down, but you can only access the one at the top right now. You can't get the one from the bottom. You probably could, but then you break your plates, right? So the idea with a stack is you can store any object. It could be ints, it could be strings, whatever, but the operations are last in, first out, right? So if I put in A, and then I put in B, and then I put in C, C is the candidate to come out first. I can't get B or A out until I've gotten C out, right? C has to come out first, yep. If you're in Python, in the one stack, you can do whatever you want. Yeah, you can store anything because Python doesn't care about types. If you were using C or something, you might then you need to take a bit more care about what you're storing. If you want to store different types, you need to store pointers to things probably, right? But yes, it doesn't really matter, especially in Python and in this course. A stack is just the structure storing the things, and the things could be anything, okay? So all you need to think of is that you do insertions at the top and removals from the top. So the ADT looks like this. You can push some element, T's arbitrary, it's whatever you want. You can pop. Pop means take the thing out, not just return it, but like actually remove it as well. Top means tell me what's on top, but don't get rid of it, right? So they're very subtly different, but they're kind of the same. This one just actually removes, but this one keeps the element. You want to know how many things there are, you might want to know if it's empty. This is a very, very simple API. So here's an example that I won't really run through. I think we can do better with our time, but I'll tell you just how to read this so later on when you look. Basically, you've got what function's getting called, what return value you're getting from that function, and then the contents of the stack. So if you push a 5, your stack has 5. If you push a 3, your stack has 5 and then 3. If you look at the size, you have 2 elements, right? If you pop, you get 3, and the reason you get 3 is because it was the last thing pushed, because it's on top, right? So that's easy. Now, if you want to implement this thing, you could use an array, right? You could use a fixed size array. You could use a dynamic array. If you use a fixed size array of some size n, what would happen if you tried to put n plus 1 things in? Yeah, you get an overflow, right? So it's easy. And then 3, what function? An example that I won't really run through. I think we can do better with our time, but I'll tell you just how to read this so later on when you look. Basically, you've got what function's getting called, what return value you're getting from that function, and then the contents of the stack. So if you push a 5, your stack has 5. If you push a 3, your stack has 5 and then 3. If you look at the size, you have 2 elements, right? If you pop, you get 3, and the reason you get 3 is because it was the last thing pushed, because it's on top, right? So that's easy. Now, if you want to implement this thing, you could use an array, right? You could use a fixed size array. You could use a dynamic array. If you use the fixed size array of some size n, what would happen if you tried to put n plus 1 things in? Yeah, you get an overflow, right? So you can't put something there. So in that case, you could throw an exception, but is there something better you could do instead of using a fixed size structure? Dynamic array. And if you can get constant time push and pop on an array, can you get constant time push and pop on a dynamic array? Yes, with the caveat that it's amortized constant time. Let me get there first. Beautiful point. So we could also use a linked list here, right? And what we could do, the insight here is that if we kept putting the thing at the top of the head, I can always put something at the heading constant time, and I can always remove something from the heading constant time. Right, you're a very good data structure designer. Yeah, okay, your assignment says otherwise. We'll see, we'll see. Okay, so that's the general idea. So in this example where they say throw some illegal state exception, that's just if you run out of space. But to me and to most data structures, designers, probably you'd be better off using something that can grow, because unless you have perhaps some really sharp efficiency guidelines you need to meet, it's always kind of okay to do amortized constant time, and that means that you'll get amortized constant time pushes, and you get constant time pops, right? So here's the performance. If you've got little n being the number of elements in your stack, and you've got a fixed size and big N, which is greater than or equal to little n, you're going to use big N space. Each operation will run in constant time. Pushing to the back just means add the element to the next free index, right? So if I've got an array, I can keep track of the current first empty spot. When I want to push, I just add the thing to the spot, I increment that pointer, and then I have my next empty spot. So that's constant time push. And then pop's just the same. I go to the last empty spot, I go back an index, I remove the thing, and then I move the cursor backwards. So that's really nice. And as I said, if you want O of 1 push, you get O of 1 push with a fixed size. You get O of 1 amortized push with a dynamic one, because sometimes a push will take linear time, right? Like we learned last week. So here's where I talk about that. Yeah, so here's where you preempted me. We could also use a linked list, right? So this is a nice place to distinguish between containers and data structures and so on. So you've seen a linked list, a kind of horrific one that's hard to implement. Sorry about that. You've also seen a dynamic array, also a horrific one that's kind of hard to implement. There's a reason Python doesn't support prepending constant time or reversing constant time, and you're learning about it. However, you could use either of those. If you wanted to build a stack today, right, or even a queue, we're going to move on to queues in a minute, you could use either a linked list or an array or a dynamic array as your underlying data container. Any of them would be okay, right? So we have a couple of options here. We can move on to queues, but I think what might be interesting is, because a lot of people haven't really implemented data structures on their own before, we could take the extensible list I showed you last week and we could turn it into a stack. What would we prefer? Do we want to implement some code and watch me flail, or do we want to just burn through the boring lecture? Burn? Burn? All right, we burn. We keep going. So queues. Queues are kind of saying the opposite of stacks is not quite true, but everybody stood in a line before, that's a queue. So first in, first out. So before, right, so with the stack, we were kind of doing this. We're going push in A, and then push in B, and then push in C, and this one is the first off. Queue is backwards. So if you put A in first, and then B, and then C, you're going to get them out in this order, right? So A will come first, because they were the first one waiting, right? So that's kind of easy. So insertions go at the back, removals at the front. That's just an implementation detail. Actually, it doesn't matter how you do it as long as it's efficient. And we'll talk about that in a sec. But here's the so insertions go at the back. Removals at the front, that's just an implementation detail. Actually, it doesn't matter how you do it as long as it's efficient. And we'll talk about that in a second. Here's the ADT. You can onqueue an element. That just is like push, put something in the queue. DQ an element, you return the element. You might want to know what the first thing is. So this is like the peak or the top in stack. You might want to check what's at the front, but not take them out of the queue yet. Okay, you might just want to see what it is. You might want to see how many things are in there. You might want to see if it's empty. Okay, pretty easy, I think. Again, you read this the same as you read the other one. If you onqueue 5, you don't return anything, you get 5 in the queue. You put a 3 in the queue grows. Couple options here. We can move on to queues, but I see and then push in C, and this one is the first off fashion, all right? So what you do is you keep variables that track the front of the queue and the size of the queue, right? And I know one of our tutors really, really hates wrapping around in arrays, so that particular tutor doesn't like this type of queue. However, it's still valid. So if you store an index to the front of the queue and the number of things you've stored, you can always figure out basically where the queue starts and ends with some modulus operators. So this is the front of the queue, this is the end of the queue, this is the next free position in the queue. But of course, as you add and remove elements, you might end up wrapping around. So in this case, the queue starts here, but actually the last element's here, right? So that's pretty simple. Again, it's just using a fixed size array as if it was a ring, like connected as a circle, and you just keep going around the ring, right? So that one's pretty cool. Operations, returning the size. Well, here's a point that I think I maybe haven't gone over enough, or maybe I have and you're sick of hearing this. There'll be two groups of people in the room maybe. When you build a data structure, you should keep track of things like how many elements are in there, the capacity, where the front thing is. Because these variables that might take 32 or 64 bits, they might save you linear time. They might turn linear time into constant time. We saw this last week when I said, would you pay 64 bits to store a pointer to a tail of a linked list, where that means that instead of getting linear time to the tail, you can get there in constant time? Most people should say, yeah, I'll pay 64 bits for that, right? So again, here, if you've got a queue, it's okay to have, hey, what index is the front at? What index is the last thing at? Or where's the next free position, right? You can keep track of stuff. That's okay. You should do that. It's how data structures become fast. Is empty is an interesting one. Yeah. Yeah, either. That's what I'm saying. So I'm saying if you know where the front index is and you know how many elements are in there, you by definition know the back index, whether it's wrapped or not, you just do a modulus. And by knowing where the last index is, you also know where the next free spot is. So storing 2 variables is sufficient to tell you where the front, the back, the next free is, all in constant. Yep. To me, here, what I would be storing is the front and the size, because both of those together would be sufficient for what I need. If you really wanted to, you could keep the R pointer, but it would just be front plus size plus 1 mod n, big N, right? So, but what I'm saying, right, the lesson is store variables. It's okay, you can do that, right? Now, again, if you've got a fixed size array and you try and onqueue something, you're going to have an overflow. So in that case, we want to throw some exception. But again, this is kind of boring because most queues you might want to grow naturally. So you can just substitute your fixed size array container with a dynamic array, an extensible array, and that's going to be okay, right? That's going to be fine. It just means that again, we need to be careful instead of saying we get linear time, whatever, it might become linear time, whatever, amortized. Okay. So another thing is if your stack or queue is empty and someone tries to pop or dequeue, what should you do? Oh, so you could throw an error. You could throw an underflow error. We might just return none, right? Implementation detail. Actually, you can do whatever you want as long as it's well defined. And when you document your data structure to your user, they understand what it should be doing, right? So let's talk about some stack and queue applications here. We're doing okay with time. So the obvious one, and I talked about this when we did recursion, is call stacks. Your computer has a call stack. The call stack essentially keeps track of which instructions are being executed where in the program, and so it knows when to return from a function, where it should go, what it should do next, right? So these are actually stacks. And basically, it's going to keep a memory address and some sort of local variables, for example, that might get passed around. So essentially, every time you run a program on your computer, there's a call stack being loaded and instructions being pushed and popped off a stack. So you're actually using these all the time without even knowing it. reversing a list is the really obvious thing you could do with a stack. So let's have a look at this example. And note here that I'm mean because I don't let you use Python lists, but a Python list actually already has an append. We know this, right? An append puts an element at the back. It also has a pop. Pop takes the last element out. So you've actually already got a stack. If you've got a Python list, they've just given you functions that allow you to do stack operations on a Python list. So what we can do here, suppose we have a list of elements coming in and we want to reverse them. We can make an empty list when we call it our stack. For each item in the input list, we can append it to the stack, right? So that's like going push, 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 push. Now hopefully you can see why it's going to be reversed because I have to get the topmost thing off, right? So the first word I push, say it's a list of words, the first word I push is at the bottom, the second word I push is above that, so on, so on. When I go to unwind the stack, I have to start from the top and go down. So it's going to come out backwards, right? That's what this code's doing. So you could do something like this while length of the stack is greater than 0, or perhaps you could just iterate until you get an exception, depends on the implementation. You could set inlist to be the element that's coming out of the stack and return the inlist. So if you did reverse here, 1, 2, 3, 4, 5, 6, you get back the reverse. Now you already know how to reverse in other ways because you did it, so who cares? Well, I care because it's a stack, but anyway, it's kind of boring, but kind of a use of a stack. So it's nice to just see that Python lists give you stack behavior out of the box. Parenthesis matching is a slightly more interesting one you can do. So if you have this problem, a really simple example of this problem would be that every open brace needs to be matched with the equivalent closing brace without another closing brace of a different one in the middle, right? So in this case, open this one, close this one, open, open, close, close, open this one, open that one, sorry. I'm sure there are names for these different brackets, but I just call them curly, square, and circle or whatever. So in this case, it's correct because every parentheses matches, but in this case, we have a close before we have an open, so that's a fail. This one we have an open without a close, so that's a fail. This one we open, circle, curly, square, square, and then in this case we have a circle and these two don't match, so that's a fail, right? Now you can use a stack to do this. It's pretty simple as well. The only thing that's different that you haven't seen is I'm using a dictionary here, and what the dictionary does is it stores a mapping between open brace and the corresponding closing brace. So what I have here is if I see this opening brace, I expect to get back this closing brace. And I can ask the dictionary, hey, here's an open brace, what should I expect to get back? And it'll give me the corresponding closing brace, right? So all I do here is build my stack, go through my string, map the string to the corresponding closing brace, right? And that's only if I've got an opening brace I do that. If I find a closing brace, what I do is check that it matches the one I put in the stack, and if it doesn't, I've made a mistake, right? So again, this is pretty simple. At the end, we just need to make sure the stack's empty, because if the stack isn't empty, it means I've still got a mismatch, and I say false. Or sorry, I say true if I don't have a mismatch at the end, if I haven't got anything left in the stack, otherwise I return false. I think this is actual Python code. I think I wrote this last year, so you can probably copy and paste it and it might run. My Python's dodgy, so hoping I'd inspire confidence in grade scope. HTML tag matching is a little bit more realistic. This same sort of brace sort of matching problem, but we're matching tags now. Again, a stack can help. So obviously, if you've got well-formed HTML, you need the matching tags they can be nested, but they have to have the matching closing tag. And of course, pretty much the exact same algorithm can be used, but you just apply HTML tags, and you can check whether your HTML is malformed. I didn't make this example, so no. What was that example that came up in the first lecture in Wikipedia? Something about communism or something? I didn't make the little boat, okay, so don't at me. So when do we see queues? Round robin scheduling may be something you've heard being a computer science student. So back in the day, even now, but even more so back in the day when operating systems could only run on a single processor and we only had one physical unit that could execute instructions. For example, when Apollo went to the moon, if you believe that happened. I believe that it happened, but I don't, you don't have to believe. So the CPU can only do one thing at once. It's a monoprocessor. And so if you've got a bunch of work you need to do, the problem is, and this is sort of an operating system thing we're talking about, the problem becomes, if I do all of the work that this person told me to do now, it might take 10 minutes. And then if I move on to the other thing, maybe the space shuttle already crashed or something, right? So I need to be careful. I need to share the processing. A round robin scheduler is just a fair scheduler that says each person or each element gets some amount of time to be serviced, and then it goes to the back of the queue and waits its turn. And you just keep cycling through the queue. So as you can see here, I take some element out, I do something with it, and I put it back to the back of the queue, and I just keep doing that. And that way everybody gets a sort of a fair share of time, right? So that's a really easy one. Later, and in fact next week, I think, you're going to see priority queues. Now, here's an interesting question, or maybe not so interesting. I don't want to get into ethics here, but if you're considering an emergency room, patients need to be triaged according to how severe their affliction is.